Hello everyone, this is unit 3rd Lebesgue Integral. So today we are doing integral of non-negative measurable functions. In this section we generalize the definition of Lebesgue integral to include unbounded functions, but in particular non-negative. So one side bound is given to us that our function is always greater than equals to 0, but the other side bound is not given to us, that may be unbounded. Right, so we are given a function which is non-negative, which is measurable, and which is defined on a set E, measurable set E, but we don't know whether the set of measure of that set is finite or infinite. That may be infinite. Right, so what we are given? We are given that any non-negative measurable function defined on a measurable set of finite or infinite measure. So the definition is how to define this integral. If f is a non-negative measurable function defined on a set E, which is also measurable, then we will define integral of f over E. Now just see clearly it is greater than equals to 0. Why? Because given that f is non-negative, so f is greater than equals to 0 means integral of f is also greater than equals to 0. So we have to find corresponding to f, we have to find those bounded measurable functions h such that h is less than equal to f. Clearly h should be less than equal to f because h is bounded and f may be unbounded. So we will always find h a bounded measurable function which is less than equal to f, and we have to find supremum of all this. So that will approximate the value of integral of f over E. Okay, so what is h? H is a bounded measurable function such that the measure of all those x belonging to E where hx is non-zero should be finite. We have to find those bounded measurable functions such that whenever hx is non-zero, the measure should be finite. So we have to vary these bounded function such that h is less than equal to f, and then we have to take the supremum of all these. Means we have to find the maximum bounded function which approximates the value of f over the value of integral of f over E. The definition is clear. What we are given? We are given that f is any non-negative measurable function. To find out the value of integral of f over E, we will consider any bounded function which is less than equal to f, right, and it is measurable such that the measure of all those x belonging to E where hx is non-zero should be finite. We have to consider those bounded measurable functions and then take supremum of all these. This will be equal to the integral of f over E. Bounded function ka measurable we have already done, that it should be defined in the terms of simple functions. Since it is bounded, it lying between some bounds, let's suppose some alpha and beta, so we will get some minimum values and some maximum values, means simple functions which are less than equal to h, simple function which are greater than equals to h, then we take infimum and supremum, and then we get the value of integral of h. But in case of a non-negative measurable function, we will consider those bounded functions which are measurable, which satisfy this property, and which are less than equal to f, and then take the supremum of all this. We will get the value of integral of f over E. Now these are the properties. This says let f and g be non-negative measurable function which is defined on a set E. Then the first property is the integral of Cf is C times integral of f over E, where C should be strictly greater than 0. Why C should be strictly greater than 0? Because our f is also non-negative. So there is no requirement of C less than. If you take C less than 0, then this function will become negative function. So we consider this to be strictly greater than 0. Now this says you can take c constant to be outside. Similarly, if you add two functions, find its integral, then it should be equal to the integral of f plus integral of g, means separately. The third property is, if f is less than equal to g almost everywhere, then the integral of f over e should be less than equal to integral of g over e. These are same properties which we have already done in case of bounded measurable functions. Now just see the proof. So now what is integral of cf over e? By definition, it is supremum of all those ch bounded functions which is less than equal to cf over e. Now c is strictly greater than 0, so you can cancel out over here. And in case of bounded, we already done that c times h is nothing, c times integral of h. So we get this is nothing but c times integral of f over e. Now let h and k be bounded measurable functions such that h is less than equal to f, k is less than equal to g, and they vanish outside a set of finite measure. Means where the measure is not finite, there the value of h is 0 and k is 0. Where the measure of this set is not finite, there the value of that functions are 0. So we consider bounded functions h and k corresponding to f and g, which vanishes outside a set of finite measure. So clearly h plus k is less than equal to f plus g. So the integral of h plus, since this is bounded, right? So in case of bounded, we know that integral of h plus k is same as that integral of h plus integral of k over e. So we can put this value over here. It should be less than equals to integral of f plus g over e. Why? Because our h plus k is less than equal to f plus g, and integral of f plus g is nothing but the supremum of all this. So this should be less than equal to integral of h plus k over e should be less than equal to the supremum of integral of h plus k, which is nothing but integral of f plus g over e. Okay, now you take supremum to both sides with respect to h less than equal to f and k less than equal to g. Since our right hand side is independent of this supremum, okay, so this inequality holds if integral of h plus integral of k is less than equal to this, so supremum of h less than equal to f, supremum of k less than equal to j will also less than equal to integral of f plus g, because this inequality holds for each bounded function h as well as k. So it holds for supremum also. Now this gives us, this is nothing but the integral of f over e, this is nothing but the integral of g over e. So we get the first inequality, that integral of f over e plus the integral of g over e is less than equal to the integral of f plus g over e. Now we have to prove the reverse inequality. So just see, to prove the reverse inequality, we consider psi function which is bounded, measurable, and vanish outside a set of finite measure. means this function attains value 0 whenever our measure is infinite, and satisfy that this bounded function is less than equal to f plus g. Now we have to define h and k in such a way such that h is less than equal to f, k is less than equal to g, and h plus k is nothing but psi. So now we define two functions h and k by setting hx to be the minimum of fx and psi x. So what will be the value of hx? It is the minimum value of fx or psi x. So clearly hx is bounded because our psi function is bounded. So we put x to be x1, then we have to find the minimum of these two, so that is the value of h. So clearly our h is less than equal to f, clearly our h is less than equal to psi, because it is a minimum value of from these two. Now we define function kx as psi x minus hx. So clearly kx plus hx is nothing but psi x. And also, since psi x is bounded, hx is bounded, difference of two bounded function is again bounded, so kx is also bounded. And third observation, so now just see, you can substitute the value of psi x from here. Our psi x is less than equal to f plus g minus h, but h is less than equal to f. So ultimately you will get kx should be less than equal to gx, right? So what we claim that hx is less than equal to fx, kx is less than equal to gx. Now this is just by the definition, since it is minimum of these two functions, so clearly hx should be less than equal to fx. Now you find out the sum of these two, you get hx plus kx is nothing but psi x, but psi x is less than equal to f plus g, and we know that hx is less than equal to fx. So what are the possibilities? Either hx attain value fx or hx attain value psi x. Now just see, if our hx is psi x, then what will be the value of kx? Put the value of hx over here, you get psi x minus psi x, so you get 0. So in that case kx is 0, and clearly kx is less than equal to gx. Okay, if hx is, so if hx is equal to fx, then clearly kx should be less than equal to gx. So corresponding to psi and f and g, we are having now hx and kx, such that hx plus kx is psi, and hx is less than equal to fx, kx is less than equal to gx, and both are these bounded measurable functions. Now just see, since h and k are bounded by the bounds of psi and they also vanishes where psi vanishes, so we have the integral of psi over e is nothing but the integral of h plus k over e, but since it is bounded, so you can separate over here. Now further, since h is less than equal to f, so clearly integral of h over e should be less than equal to integral of f over e, because this is the supremum one. Similarly for here, right? So what we get, the integral of psi over e is less than equals to integral of f over e plus integral of g over e. So from this inequality, just see, this holds for all those psi which are less than equal to f plus g. Since our right hand side is independent of psi function, and this inequality holds for each bounded function psi which is less than equal to f plus g, so we can take supremum to left hand side. This also holds. Now this is nothing but the integral of f plus g over e. So now we are having the reverse inequality. Combine these two inequalities, we will get the proof. So clear to everyone that the sum of functions, the integral of sum of two functions is equal to the integral of first plus integral of second. Now third part you can do yourself. So similarly complete the third one. That is just by the definition. Now this is a problem. You have to solve this and we will discuss it. The problem is, let f be any non-negative measurable function. You have to show that f is equal to 0 almost everywhere on E if and only if the integral of f over E is 0. So clear? F, what is f? F is non-negative measurable function. But we have to show f is 0 almost everywhere on E if and only if the integral of f over E is 0. This we already done in case of bounded functions. And here it is also given f is greater than equals to 0. So you can prove it yourself.